When we have sine raised to some power and cosine raised to some power, and these two functions are multiplied together and we need to integrate it, this is a strategy to use. Look for the function that has the positive odd power. We save one factor of the function, put it to the side, rewrite the same function as the other trig function, using the Pythagorean identity, sin² plus cos² equals 1. So if the odd power is on the sine, then we save a factor of sine, rewrite the remaining sine in terms of cosine. If cosine is the one that has the odd power, save a factor of cosine, then rewrite the remaining cosine in terms of sine. After doing these conversions to the integrand, we integrate by 𝑢-substitution. Solve the integral sin³ x multiplied by cos⁴ x. The sine function has the odd power. Save a factor of sin x. Rearranging the Pythagorean identity, we can bring the cos² to the other side in order to isolate sin². Rewrite the sin² into a 1 minus cos². Most of the integrand is now in terms of cosine, except for that sin x that we saved. Apply 𝑢-substitution. Let u equal cos x, differentiating both sides. du is negative sin x dx. And then isolate the sin x dx. Just move that negative sign to the other side with du. Everywhere where we see a cosine is now a u. The sin x dx becomes a negative du. We can expand everything and integrate as a polynomial. Multiply that u⁴ through. And there's that negative sign. I'm always forgetting negative signs, so let's multiply that negative sign through as well, just so we don't have an extra factor of a negative just floating somewhere in the function. We have negative u⁴ plus u⁶. Stylistically, it might look awkward to have a leading negative sign, so flip it around so that we have a positive u⁶ and then minus u⁴. Honestly, if we didn't flip it and left it as negative u⁴ plus u⁶, it's also correct. Integrating the u⁶, we raise that power by 1, divide by the new power, u⁷/7. And then u⁴, similarly, raise that 4 to the 5 and divide by 5, plus the constant of integration. We started with the x variable, we should also go back to the x variable. Everywhere where we see a u, replace that with a cosine x. We have a similar integral except that the powers are flipped. The power of 4 is now on the sine and the power of 3 is on the cosine. But the workflow is more or less the same. The function with the odd power is cosine. Save a factor of cosine. Rewrite the cos² in terms of sine. Using the Pythagorean identity, we can rearrange for cosine² as 1 minus sin². The integrand is now in terms of sine except for that cosine we saved. Let u equal to sin x. Differentiating both sides, du is cos x dx. Making the substitution, the sin⁴ becomes a u⁴, 1 minus sin² becomes 1 minus u². Cos x dx is du. Distribute that u⁴, u⁴ minus u⁶. And integrate as a polynomial. Raise the power by 1, divide by the new power, u⁵ over 5, u⁷ over 7, and add the constant of integration. Get back the original variable. Everywhere where u appears is now a sin x. This question is interesting in that both trigonometric functions have odd powers. So which one do we pick? Let's just pick one and see what happens. Sine has an odd power. We can save a factor of sine and then turn that sine into the other trig function, into cosines using the Pythagorean identity. Sin² is 1 minus cos². But in this case, we have a sin⁴. That means we have to square that sin². So we actually have to go 1 minus cos², the whole thing squared. Let u equal to cosine x, then du is negative sin x dx, and isolate that sin x dx as a negative du. Everywhere where we see a cosine is now a u. The sin x dx is a negative du. Expand the integrand. In this case, we have a 1 minus u², the whole thing squared. We have to FOIL that out. 1 times 1 is 1. 1 times negative u², then we have another negative u² times 1. Altogether, we have negative 2u². And then negative u² times negative u² is a positive u⁴. Distribute that u⁵. Personally, I also like to distribute that factor of a negative 1. And we're ready to integrate this polynomial. Raise the power by 1, divide by the new power. The u⁵ becomes a u⁶, and then divide by 6. The u⁷ becomes u⁸, then divide by 8. And u⁹ becomes a u⁻, then divide by 10. Add on the constant of integration plus c. The 2/8 can be simplified as a 4 in the denominator. Get the original variable back. Replace all of the u with cos⁵. We can redo the question by choosing cosine as the trigonometric function that has the odd power. Save a factor of cosine, and then rewrite the cosine in terms of sine. Cos² is 1 minus sin², but because we have cos⁴, we have to square that quantity. So the entire thing, 1 minus sin², the whole thing squared. Letting u equal to sin x, then du is cos⁵ dx. Make the substitutions. And expand. The 1 minus u², the whole thing squared, we can expand that as 1 minus 2u² plus u⁴. Distribute that u⁵, and then integrate the polynomial. The 2/8 is a 1/4. Back substitute. Everywhere where there's a u is now a sin x. Our two answers look a bit different. We can graph our answers on a graphing calculator like on Desmos to verify our answers. The two curves should be parallel. The difference is that plus c. If we move a curve either up or down by 0.016666 units, we would in fact have overlapping curves. So yes, our two answers are both correct. Which method do you prefer? I prefer the method that lets u equal to sin x in order to avoid that negative sign. When we do 𝑢-substitution, sin x differentiates to cos x, but cos x differentiates to that negative sin x.